Hi, everyone. We're going to start chapter 5, which is a completely new direction for this course. Up until now, we've been doing a lot of chemical reactions, and now we're going to take things that are more smaller scale. So we're going to go into the world of quantum chemistry. And I don't want the term quantum to scare you because it is a very, what's the word? It's like not a trendy term, but it's a term that you often hear when you want to sound smart or when you're reading something complicated or whatever. But it's not, and it's at this point where you have to start learning about it and then get into it in more and more detail as you go into further studies. I'm going to briefly introduce this idea of waves and why waves have to do with quantum chemistry. But there is actually a course that you guys will be taking in your fourth semester at the school, and that one is strictly about waves. It's called Physics of Waves, and we go into all these topics in a lot more detail. So the first thing we should tackle is this idea that light can behave like a wave, and we've heard of like having different wavelengths of light. Ultraviolet is a shorter wavelength, and then as you get a little bit longer, you get into the visible light, and each color's got different wavelengths. And then you have the radio frequencies and things like that. And those all refer to different aspects of light, or light being emitted at different wavelengths. So for all intents and purposes, we've accepted light as a wave for a long time. And so the characteristics of waves are pretty straightforward, and I think you might remember some of this from high school math class. And the first things first is when you're shown a wave, one length of a wave from a peak to a peak is referred to as a wavelength. And from the equilibrium point, which is this black dotted line here, to one of those peaks, it's called an amplitude. Another thing that you might hear of frequently is this idea of frequency. So that's basically how many oscillations will occur every 1 second, and that's a measurement of hertz, if you remember that from your math class, hopefully. And then we have this idea that wavelengths of light are somewhere between 400 and 800 for everything that's visible. All right, so this is the range of visible light, range of visible light, with everything above that in the infrared and the radio wave region, and anything below that in the ultraviolet and the X-ray or gamma ray spectrum. And all of that takes place, and all of that is a part of the electromagnetic spectrum, which is this huge range of different wavelengths and or frequencies of light, and they all represent different things. And so as you get smaller in wavelength, all right, so if the wavelength is really small, then what you have is actually a higher frequency because you have more little oscillations. But if your wavelength is high, right, or if your wavelength is long, then you have a lower oscillation frequency, so less cycles every second. And so if you're going to talk about the spectrum of light, this usually refers to a high energy, because you have to do a lot of little ups and downs in a little bit of time. And this refers to as low energy, because it can take your time and go at slow wave. Okay. And so this side is low energy, and this side is actually high energy. And the way I remember it, and I guess everyone has their own trick, and the way I remember it is that I have light, which is made up of purple and red on each end, and infrared is stuff that you use in your remote control to control your TV, let's say. Microwaves are the things that you use to heat up your food, and radio waves are things that you might use to listen to like a podcast or something, or anything that's giving you Wi-Fi is considered to be a radio wave. And none of those are very harmless. None of those are harmful, they're very harmless. So they're low energy. And ultraviolet and X-ray, well, ultraviolet, where, we protect ourselves from it by using suntan lotion. X-rays, you have to put this big leather jacket on it, on yourself to protect yourself against X-rays when you go to the doctor to get an X-ray on your broken bone or something like that. And gamma rays are actually what we use to kill cancer cells. So those are quite dangerous rays, and therefore they can be considered to be high energy. Okay, that's my little trick of remembering it. I mean, it's not really a trick, it's just kind of like a reminder as to which one's the dangerous one and which one's the non-dangerous ones. And this one is called ultraviolet, and it corresponds to it being just above the violet region. And this is called infrared because it's considered to be just below the red region. Okay. So every wave can be described with both frequency and wavelength, and all of that depends on speed. And in this topic, we're going to be using the speed of light as our frame of reference. And the speed of light is constant. It's always this velocity. And because of that, if this is constant and we have that the frequency is equal to, well, the symbol for frequency, according to this, is, I don't know, my eraser's not working. Sometimes my computer does this. Okay, I'll try not to erase, but that might be a bit annoying later. But C, if it's constant, is equal to frequency multiplied by wavelength, and frequency has a special V symbol for H. See, now I have to cross it out again because my eraser's not working. So C is equal to lambda, which is wavelength, multiplied by frequency, which is this special Greek letter V. And this is wavelength. And this is frequency. And if C stays constant, then when you increase wavelength, you have to decrease frequency, and vice versa. If you increase it, if you increase frequency, then you have to decrease wavelength. So that's what I mean where I say that if it's a high frequency, it's going to be a low wavelength as a short wavelength, and if it's a long frequency, a huge wavelength, then it's going to be a small frequency. There's very few oscillations per second. And so you can characterize every type of electromagnetic radiation, whether it's low frequency or high frequency. You can describe it as both a wavelength or a frequency because it's always associated together with this constant C. Okay, so in this case, you say light blue glow given off by mercury street lamps has a frequency of 6.88 hertz. What is the wavelength in nanometers? So you can express it as a frequency, or you can express it as a wavelength. So wave has always been given to us as this idea that it's, light has always been given to us as this concept that it's a wave. All right, and in order to understand quantum stuff, though, well, this is an experiment that proves that light is a wave. You don't need to know too much about it because we're going to talk about it more in your waves physics class. But more recently, it's been discovered that light is not only a wave, light also behaves like a particle. And this is where the quantum world comes into place. And I don't mean quantum world like they did in Avengers, Infinity War, and what was the last one called? Endgame. Avengers Infinity War and Endgame, where they had to go into the quantum world. I don't know, spoiler alert if you haven't seen it, but come on, it's been 2 years already. The idea that light can behave like a wave, but also now light can also behave like a particle. And there's always this struggle between the two. Is it a particle or is it a wave? And so Einstein came up with an experiment that basically showed that it is behaving like a particle. Not that it's not behaving like a wave, but that it is definitely at least behaving like a particle. And so he showed this experiment. I'm not going to explain it here, but essentially the analogy is, I'm going to use this image here to kind of bring that forward, that a baseball, regardless of how hard you throw it at a window, it's only ever going to break one window. And if you throw it harder, you're just going to break that window and the pieces go flying faster. Okay? It's if it were a wave. So that's the analogy. Okay, so now light can behave like a particle, where each little wave particle can has its own packet of energy, can be used to dislodge an electron. So this experiment that Einstein created made it so that his electrons, or not electrons, his photons that he was shining onto a metal plate would cause electrons to eject themselves. All right, so one photon caused an electron to eject itself. One baseball caused the window to break. Okay, so that's the analogy there. If it were a wave, then the amount of light that he would put on, that he would shine onto it, would just generate more and more breakage, more and more electrons to eject. But what ended up happening was that the higher the frequency of the lights that he would put, just the faster the electron would get ejected. It's a bit of a complicated experiment, and I don't expect you to understand it on my little 2-second slide here, because we're going to be spending like at least a whole hour on this in your physics course. But suffice it to say that Einstein came in and showed that light can be described as a single packet of energy. And this idea that things could be packaged into these one individual packets is what quantum mechanics is about. Everything, not quantum mechanics, quantum physics. That's what quantum physics is about, is this idea that things can be in these discrete packages. Whereas a wave, if you think about it, it's just like a continuous flow of energies, of ups and downs and everywhere in between. Whereas quantum, it's like on, off, on, off, on, off, like this discrete packets, okay? All right, so this is the continuation of that explanation. You don't need to know much about this. Again, the important part is that if you wanted high energy electrons being ejected from the plaque, you would have to just increase the frequency of light, not give it more light. Again, not so important in the realm of what we're talking about here. So Einstein, actually not Einstein, Planck, one of the people who inspired Einstein to come up with his experiment, designed this equation to show that light, the frequency of light, can be converted into energy. Okay, and so here it's that energy is equal to some constant, which is called the Planck's constant, multiplied by the frequency of light. So if this is a constant, then it's basically, you can say that energy is proportional to the frequency, because there's a constant there that's making it an equality. And that's very interesting, because up until he came up with this equation, you kind of understood that light was a wave, and that the wave carried energy with it, but never that a particle, or not a particle, but a photon itself carried some amount of energy onto it. And so that energy can be quantified using this equation. You can actually calculate it in joules, and that becomes like a huge thing that exploded the world of quantum physics. Again, bear with me, it's not so important right now. So now that I've hopefully convinced you that light can be a particle, we can take advantage of that. And taking advantage of that is quite interesting, because it allows us to identify atoms and their identities in a certain way. And so this is how it grows into this world of chemistry. I'm going to come back to this in a second. And so what I wanted to explain was that we had this model that you guys are probably familiar with, is the Bohr model, whereas an atom kind of looks like this, all right? And this has got different energy levels, n equals 1, n equals 2. And we're going to use this because these are different energy levels, and so the more you go up, the more energy the electron, let's say I have an electron here and an electron here, this electron on n2 is a higher energy electron. And so how does that relate to waves? Well, here it is. So electrons can go up and down on these energy shells, and as they go up, they are higher and higher energies. And when an electron comes down, they go into lower and lower energy. So when you say that an electron is at its ground state, that means that it's at an n equals 1. Or n equals 1 is not there, it's actually there. I would erase that dot, but as you know, I can't erase right now. And so the energy levels are going to jump down and down and down into the closer and closer to the nucleus as they drop in energy. Now, if I shone some light into this atom, this electron here is going to absorb some of that energy, right? And then it's going to jump up to the next level. And so if I had a whole bunch of different frequencies coming in this direction, all right, and the energy of this particular one was absorbed by this electron, then the energy, the light that you see on the other side is going to be missing this wavelength. Okay, so let's say this was 400 nanometers, 500 nanometers, 600 nanometers, 700 nanometers, and 800 nanometers. On the other side, you would see 400 nanometers, 500 nanometers. You won't see 600 nanometers because it was absorbed by this electron. And then you would see 700 nanometers and 800 nanometers. All right, and so that gives you this concept that like a piece of light is missing. So if I go back to this is what that represents. So if I were to shine white light onto sodium, all right, to energize its electrons, it would give me these two bands, which represents the wavelengths that it absorbed and it didn't let through. Okay, this is called the line spectrum. And so if it absorbed that, then you can kind of determine what was the amount of energy. If you know what the wavelength is here, you can figure out what was the amount of energy required to excite that electron, because as we know, E is equal to hv for the energy associated to that wavelength. All right, so these electrons, they can jump up and down from any energy level. So they can go from, this diagram is showing all the energy levels going down, but just as they're going down, they can also go up in the opposite direction. So let's say an energy, I have an electron here on n is equal to 1, 2, 3, 4. So this is on n is equal to 4. It could jump down to 3, it could jump down to 2, or it can jump down to 1. All right, and as you can see here, I have my 4 here that's able to go down to 2, it's able to go down to 3, and over here is able to go down to 1. All right, and each of those jumps is associated with a different energy level. And so if you actually look into it in more detail, you get this huge spectrum of possible jumps, basically. So going from 4 to 3, from 4 to 2, from 4 to 1, from 3 to 2, from 3 to 1, from 2 to 1, and so on and so forth, depending on how many energy levels it has. So for a more complex atom that has many electron shells, you're going to get a huge amount of these lines called spectral lines. So there's a way to calculate the wavelength that an electron is required in order to jump up or down in that spectrum. So it'll absorb the energy when it wants to jump up, and it'll release that energy when it comes down. And so what is that energy associated with? Well, it's associated with the wavelength, and as you know, wavelength is associated with the frequency because of C is equal to wavelength times the frequency. And as you know, that the frequency is also associated with energy with this equation here. All right, so when I say wavelength, indirectly I'm saying energy. So it's just a matter of a little bit of arithmetics to get there. But essentially, the energy can be calculated with this constant. It's called the Rydberg constant, and the correlation between the outer shell and the inner shell. Okay, so M2 is the outer shell, or not M2, but M is the outer shell squared, and N is the inner shell squared. Okay, well, actually, in this equation, they have it backwards. M is the inner shell, and N is the outer shell. Sorry. So this is referred to as the Balmer series, and then Johannes Rydberg actually generalized that equation. So Balmer made it specific for hydrogen, and this was his. Actually, I don't know if it's a him or a her. I'm guessing it's a her. I could be wrong there. But Balmer essentially described this equation for hydrogen because it only has 2 energy levels. But then Rydberg generalized this to any energy level here. And this here is that Rydberg constant. So I'm going to stop there because that was quite heavy, and it's kind of also unrelated to this next topic. I understand if you guys find this a little bit complicated, but it's okay. It's not one thing for sure is that it's not a big part of this course. It's just kind of the introduction to what we're about to do in the next few lessons. I would say the most important things to understand going into what we're going to talk about next is this idea that light is quantized, meaning that there can be packaged energy into these small packages, a part of matter for all intents and purposes, that have a certain wavelength associated with it. Okay? All right, so I'll see you in the next video.